So hello everybody, good morning. My name is Katarzyna Krupa and as it was said by our chair, I'm from the Institute of Physical Chemistry. And first of all, I would like to thank the organizers for inviting me to present this talk. The title will be Fiber Lasers, Ultrafast Dynamics and Applications. Even though it is a little bit different subject than the main subject of this conference, I hope that it will be interesting for you. And the work and the results that I will show, they were done in, since it will be quite different examples, so they are done in collaboration between Poland, France, Institute of Limoges and Spain. Okay. Okay, so as you know, lasers are today widely used in our daily life and are becoming the key enabling technology of the modern world. So here you have some examples of the applications of the lasers. So you can we use the laser for sensing, metrology, medical diagnostics, imaging, spectroscopy. And even though the first laser was demonstrated more than 60 years ago, lasers are the subject of constant ongoing research with growing demand for versatile and robust laser systems. So still we try to improve the performances of the laser to feed the applications. Okay, so here you can see that there are different types of lasers. So they are systems which are based on the free space optics and solid state lasers, like it was shown in the previous presentation, also on the OPO. And then there are other types of lasers which are based on fibers. So I will focus on the second part, on the fiber lasers. And the advantage of fiber lasers is that in comparison to free space, so here as you can see, they are much more user-friendly because they are more compact, they don't need adjustment and alignment. As it was said before, it can be problematic for using them. And then they are also environmentally insensitive, especially the one which are based on polarization maintaining fibers. So they are much more simpler from the user point of view. And so from this reason, nowadays they are becoming a new standard for industry and also academic research. But fiber lasers are not only interesting from the point of view of applications, but also from the point of view of fundamental research, because they are a very nice tool to find and to investigate different nonlinear dynamics and ultrafast interaction between pulses. Because today I will focus on the pulsed lasers. Okay. And so during this talk, I would like to divide my presentation into parts. In the first part, I will show how it is possible to get access and to use the ultrafast dynamics in fiber lasers. And in the second part, I will focus more on, we can say, on the application, because I will show how we can use nonlinear optics to develop and to develop new lasers, and in particular for the application to nonlinear imaging and spectroscopy. So I will first start from more fundamental part. So in fiber lasers we have the balance and interaction between nonlinearity, dispersion, gain and loss, and this makes that depending of course on the conditions, on the cavity, on the design, we can have a lot of, as I said, different dynamics. And ultrafast dynamics, because so from the application point of view, what we would like to have is that each consecutive pulse is the same, so there is a stable operation. But it is not always like that, and fiber lasers can have very different dynamics, like we can find the soliton explosion, breeders, rogue waves, modulation instabilities, and many other effects, which, as I said, it is something that we don't really want for applications, but from the fundamental point of view they are very interesting because they show us the complexity of the system and the physics, and then we can also more understand how the laser works and what to do or to improve or to remove these effects or to have them if you would like. Okay, but there is one little problem which comes with this ultrafast dynamics, that if we want to characterize the laser and we use the standard methods, like for example optical spectrum analyzer, autocorrelator, so they give you the characterization is time averaged, which means that we don't really have the access to the ultrafast dynamics, even with the oscilloscope, ultrafast oscilloscopes, because if we talk about femtosecond laser, so ultrafast oscilloscope, the resolution is too low to see these dynamics. But in 2010 it was published a paper. In 2007 it was published a paper that was talking about the real-time experimental observation of spectral instabilities in supercontinuum generation in optical fibers. And this real-time experimental observation was based on the technique which is called dispersive Fourier transform. And from this time, people also started to use this technique for the lasers, to characterize the lasers. And so what is this technique? So as you can see here, this technique is now very often used. I think that one of the reasons is also this, that it is quite simple and quite easy to implement. Because what we need is, we need some dispersive element. So in our case, we use a fiber. And if we take this fiber long enough, so we accumulate the dispersion, at the end of the fiber, we have that each wavelength is arriving at different time. And so like that, with our oscilloscope, we can map the spectrum of the spectrum of the pulses in a temporal waveform. So we have, for example, like it is here, not the pulses that we see the spectrum, how it evolves at each cavity round trip, so the shot-to-shot evolution we can find. And so like that, people started to use very often, very intensively this method. And recently, so I don't know, maybe 10, 15 years, they observed experimentally many different ultrafast nonlinear dynamics that before was not possible to observe experimentally, but only in numerical simulation we could predict that they sometimes should happen. For example, here we have one. For example, here in this we can see that if we have two femtosecond pulses, which are close to each other, and so they are bounded, and we can see that at some conditions we can observe that the phase between them is oscillating. So here is the phase is growing. And also we can have, for example, access to how the pulse is built and so on. So this method is very nice and gives us the access to new insight in the dynamics. And now I will focus a little bit more on our quite recent results, which is called double Hopf bifurcation dynamics. That also we saw in the laser. And here, so as I said, so this is the regime. So here we have a round trip on the x-axis, and on the y-axis we have the wavelengths of the spectrum, and we can see how the spectrum evolves. And of course, if you would like, as I said, to use the laser for the application, we would like to have this regime. So when we see that the spectrum is stable, nothing happened. But then it turns out that this stable regime is only working for certain parameters. But then when we change, for example, here the parameter that we change is the pump power. And so if we are slightly below the stable pump power, the threshold for the stable pump power, we can see that the spectrum is not anymore stable, but that it evolves, so it evolves periodically. Here there is, so we have the first Hopf bifurcation, which triggers us the oscillations. And here, as we can see, the frequency of this breeder is stable, which means that the period is with the time is not is the same, is fixed. And this dynamics it was confirmed and also found by several groups. But then what we found is that we can have also the double Hopf bifurcation, so the second bifurcation, which means that our frequency, our fixed frequency breather is now not anymore fixed, but it is modulated by another one. So it means that our spectrum is modulated with a period which is changing with the time. And yes, and this is interesting behavior because, I mean, from let's say two reasons. So one, because we can find that because it is the double bifurcation, and then if we continue more, we can have also bifurcation diagrams of the 3, 4, and so on. So we can see that this behavior is universal, and we can find in many physical systems. In microresonators, for example, it was found, but also in our daily life, like for example in the dripping faucet. We can find, so here, okay, I could put a video, but anyway, it's similar. So it is quite amazing to see this. But then from the other side, it's also this to observe experimental this effect is also interesting because it tells us that the lasers and the gain medium, the model for the gain medium that people normally use for simulations. So here we used ytterbium, so it's 2-level. It's maybe it is too simple. And finally the lasers are more complex that we think, because we were not with this standard model we were not able to predict our double bifurcation. Okay, so this was the first part that I wanted to show that fiber lasers and lasers as itself they are interesting also for the basic science, but also. So now I will move to the second part, and as I said, I will show how we can use nonlinear effects in fiber lasers to advance our technology, and in particular for nonlinear imaging, because our goal was to use the laser for nonlinear imaging. Okay, and so as you know, fiber lasers understood as fiber oscillators that I was talking just before, are limited in operating wavelengths by currently available gain media. So when we build the fiber laser, the fiber oscillator, we are restricted in the wavelengths that they can provide. So for example, we can have, so the most typical is at 1 micron and 1.5, so now also for 2 or for 0.9, so the recent advancement also. But if we would like to have the wavelength which are outside this quite narrow spectral bandwidth, which we would like to have, for example, for nonlinear imaging and spectroscopy, we need to do something. So the common solution is in fiber lasers is to use the nonlinear frequency conversion. Okay, so here. And now, okay, again, we have many different nonlinear frequency conversion, as you can see here. So surface modulation, supercontinuum, which are mixed of many effects. So solid on cell frequency shift, 4-wave mixing, and so on. And what I will now focus on is the 4-wave mixing effect, because this effect is allowing us to directly convert the pump wavelengths to the quite selective band. And when we when we create the cavity, so also to have the quite high power, as I will show. Okay, so briefly, what is the 4-wave mixing? So the 4-wave mixing is a nonlinear effect which converts the pump wavelengths in an upshifted and downshifted two wavelengths, signal and idler. And then to make its effect efficient, we need to satisfy here these phase matching conditions. And how we do this in fibers? So the typical way so since the phase matching conditions mostly depends on the dispersion of our fiber, and since if we talk about the fibers and the dispersion, so if we would like to tailor the dispersion and fit and satisfy the phase matching conditions, so also to fit with the pump that we have, the common the easiest way is to use photonic crystal fibers, which looks like that. So we can have this this whole structure, and depending on the structure, on the diameter, and on the distance between the holes, we can shift the dispersion and fit with our phase matching conditions. And so the thing is that with four-wave mixing also, because of that, it is quite interesting, because with four-wave mixing we can, so here we have the phase matching diagram, we can have a quite wide tuning of our new generated wavelengths. So when we tune a pump, here when we tune a pump wavelengths, we can tune the wavelength on the phase matching of the four-wave mixing, and this is a standard method to tune. So here we have the very nice laser source that was in the last several years developed by the German groups. And so here I will not talk in details about this laser, but so as you can see here, so here we have the two beams and one tunable, the second, so here is the pump, here is the signal. And we can, as you can see, you can cover the whole range, including the fingerprint and CH region. That is very nice for nonlinear imaging, for SRS, for Raman stimulated scattering. So, for example, here we can it was successfully used for imaging. But what I want to say here is that this laser is based on the tunable fiber oscillator. So we tune the four-wave mixing by here tuning the fiber oscillator. But it turns out that fiber oscillators that are tunable, especially in a quite like in this quite wide range, they are not common, and they are also in the market not very easily found. So that's why in our research we were focused on, we wanted to see if it is possible to, how it is possible to obtain similar results. I mean, similar results meaning the source widely tunable based on four-wave mixing, but using the oscillator which is not tunable but a fixed wavelength. And so I will now present the two cases. I hope I will have time. So here is the first source that we developed. So as you can see here, we have the fiber oscillator which is at fixed wavelengths at 1030, and then, but still in this case, to tune the four-wave mixing, we needed a tunable pump. But this tunable pump we didn't do by tuning the oscillator, but we did after the oscillator, meaning here by using here this PCF. And so as you can see here, with photonic crystal fibers, which is pumped by amplified oscillator, we can broaden, when we increase the power, we can see that we can broaden the spectrum. And then, once we have this broad spectrum, we can filter with a tunable filter, then amplified, and so at the end, we have tunable pump with power enough to generate four-wave mixing, with a range which was similar to the setup that I previously showed, but which is based on the oscillator at fixed wavelengths. So here you can see that we have the four-wave mixing, which is tuned from 720 to, let's say, 950. Okay, so this was the first case. Then we developed also the method which does not need at all the tunability. The oscillator is at fixed wavelengths, but also the pump is at fixed wavelengths. So how we do this? We combine our photonic crystal fibers where we generate four-wave mixing with a standard fiber which we placed before this PCF. And what we didn't tune the wavelength, but we didn't tune the pump wavelengths, but we tuned little bit the duration of the pulses. Okay, and so here we have the results. So we can see that when we tune the duration of the pulses, we can tune the four-wave mixing sidebands. And the range of this tunability is very similar to the standard method when we tune the pump. And the question now is how we do this, how it happens that without tuning the pump wavelengths we can still tune the four-wave mixing, which is not at all the typical case. Okay, so here we have the numerical simulations. So to compare, the first one is done with 3 picosecond 5 pulses, and the second with 4 picosecond with the same peak power. And what we can see is that when we look on this blue spectrum in the two cases, so here also when we look on the pictures, we have first the standard fiber and then after the PCF, and we can see that in the with the first standard fiber, by pumping it with the pump at fixed wavelengths, we generate the self-phase modulation, this self-phase modulation is different. The broadening is different for the different pulse duration, and we can see that if we tune even little bit the pulse duration, we see that the thickness of this self-phase modulation is different, and since for generating four-wave mixing, it is the four-wave mixing is much efficient when we are closer to the zero dispersion wavelength of our fiber. So here, even for example here, if the spectrum is broad, what is generating, so what is giving us this four-wave mixing is this the outermost redshifted lobe. And since if we change the pulse duration, we can see that we change the spectral position of these lobes. And so if we put our results on the phase matching diagram here, we can see that our results quite well fits with the diagram, which confirms our hypothesis. Why it happens is that the outermost redshifted peak of SPM can play a role of tunable pump. So we don't have a tunable pump, but by self-phase modulation we generate it somehow. Okay, and then so just rapidly we put this source in the Cars microscope, and because we wanted to see if we can generate, if we can use this for selectively imaging the sample. And we imaged the sample, which is shown here. So the sample is composed of the polystyrene beads and the droplet of paraffin. And by tuning the pump the wavelengths of our source, we can see that we could selectively image, here there is polystyrene beads, and here the droplet of the paraffin. Of course, here we can have also the low intensity polystyrene beads, just because when we look on the spectrum of this Raman spectrum of this of the polystyrene beads, it has also a peak at the same position, like smaller peak at the same position as paraffin droplets. So this is just the reason why we see this here. Okay, so yes, I'm in time. The message to take home is maybe that fiber lasers, yes, are interesting from both sides, from the fundamental and applied research. So if we would like to go more into application and build a new lasers with the new performances, we need to start from the basic research and understand the physics. So I would like also to acknowledge our finding agency, and thank you for your attention.
Okay, right on time. So we open the session for questions from the audience. Okay, here we need the microphone. Your hand.
Very nice presentation. I was wondering, do you also have the plan to measure molecular systems? Like, is it possible? I'm a theoretician, so I'm not sure if it's a right question, but also, besides fundamental research, can you also do molecules?
But what do you mean by?
If you can use this setup to measure a system, like besides the
So we more plans because what I shown, especially the last one, so it still require improvements because as you saw the spectrum is quite broad, so we need to make it more selective and also increase the power. So our goal is more to use for imaging, at least for the moment, because we have the microscope, so we can quite easily implement in there. So it's more for imaging. Let's say we had recently a project which was now finished to measure the leukemia cell, but yes, it's more for to make a demonstration that it works.
Okay, yeah, interesting. Thank you.
Are there further questions? No? Okay. So with this we will move. We will thank you again, and we will move to the next speaker.